recording before I forget. So I guess I'll start off with, I've graded about half of your tests, and I'm hoping to get to the rest of them tomorrow. And I'll send you guys an email out afterwards with statistics and stuff. And I also want to know if you can see like my feedback or comments, if you can review your tests. So keep an eye out for that in the next couple of days. Any questions before I start Chapter 4 lecture?
I don't have any at this time.
Okay. I am just loading the lecture notes. Sharing. And there they are. So the first part of this chapter is all about chemical bonds, ionic and covalent bonds, which is something in like chemistry that is so basic and fundamental to me as a science major and a scientist for years and years and years that I sometimes forget how difficult it is for students when they're first learning. So if you're struggling with it, the key, as with everything basically in chemistry, is to just practice, practice, practice. So I did post some practice worksheets under supplemental stuff. So, and they have answer keys. At least one of them has an answer key. And there's like 97 problems in the homework, but they're like kind of quick problems. But the idea again is just to like drill in that practice, practice, practice. So we spent a lot of time thus far in the class talking about atoms, talking about the structure of atoms, and then talking about the different subatomic particles, different isotopes, different electron structures. And, but there's only 118 or so different types of atoms. Well, I guess there's more if we count all the isotopes. There's 118 different elements. So there's maybe hundreds of different types of atoms, but there are millions of different types of compounds. So compounds are made up of two or more elements in definite proportions. So, for example, we have H2O is water. It's 2 hydrogens and 1 oxygen. You can't have a compound that has different, like varying amounts. Like there's no such thing as a water molecule with 3 hydrogens or a half of an oxygen, okay? It's always 2 hydrogens for every 1 oxygen. Those are definite proportions. Excuse me. Compounds are held together by chemical bonds, and we'll talk about the 2 types of chemical bonds, ionic and covalent. And properties of compounds are different than the properties of the elements that compose them. So the classic example here is sodium and chlorine gas, all right? They combine to form sodium chloride, a compound, all right? Sodium is a metal. It's a very reactive metal. It's in group 1 on the periodic table. It's an alkali metal. If it even like has a sniff of water, it will explode. Chlorine gas is very, very toxic and also very reactive. It's a halogen. So both of those things by themselves are incredibly toxic, incredibly dangerous, and highly reactive. But when they get together and form a compound, sodium chloride, it's a pretty inert substance, and it's something actually that we require in our diets and is fairly harmless except for in very large quantities. So totally different properties that the compound has, nothing like what the elements have. So the other thing about compounds is they can't be separated by physical means. They can't be physically pulled up in any way. They can be broken through chemical means, through chemical reactions though. So the 2 types of compounds, how do I move this? There we go. The two types of compounds are ionic and covalent. So the first one is covalent. Covalent compounds, which are made of two or more atoms that are connected by shared electrons. All right, so in a covalent bond, two atoms come together and they overlap their electron clouds so that they're sharing electrons. So one covalent bond is actually sharing two electrons. I'll go ahead and set the stage for that. One bond equals two electrons. All right, covalent bonds occur specifically between atoms that are of nonmetals. So it occurs between a nonmetal and another nonmetal. Or also sometimes metalloids can get in on those. So it's two nonmetals will get together and share electrons. Covalent molecules or covalent compounds form molecules. All right, we call the individual units of covalent compounds molecules. The other type of compound are ionic compounds, and these are made through transfer of electrons. So you have like a sodium atom that has one valence electron, but it really wants to be like a noble gas and get rid of that valence electron, and chlorine that has 7 valence electrons and could use one more. So sodium transfers its electron to chlorine, and now you have a sodium ion. It has a positive charge because it has lost an electron, and you have a chloride ion that has a negative charge because it's gained an electron, and now they are attracted to each other through their opposite charges, and that attraction is the ionic bond. Okay, so for ionic compounds, they are generally composed of a metal and a nonmetal. Because they have to be composed of an anion and a cation. And if we remember the trends from the periodic table, metals on the left side of the periodic table have less than 4 valence electrons, and they tend to lose them and form cations, whereas nonmetals on the right side have a lot of valence electrons and they will gain and form anions. So metal cations and nonmetal anions make for great ionic compounds. They don't form molecules though. So what happens when you have a bunch of ions is they form a lattice structure. All right, and so we don't call the individual units of an ionic compound molecules. People will, like wrongly, I will. Textbooks might even sometimes, but technically they are called formula units. Okay, so this little diagram down here just kind of shows you molecularly what's going on. So in a covalent compound like water, you've got H2O, 2 hydrogens bonded to an oxygen, and then if you have a glass of water, what you have is a bunch of individual water molecules floating around, moving around each other. All right, but sodium chloride, when we make salt, sodium chloride, there's no such thing as like a sodium chloride molecule. You don't have like little individual sodium chlorides like bonded together floating around ever. All right, what you have is a lattice structure, a giant crystal that's made of lots of sodium and chloride ions bonding with each other. And so we say that one sodium and one chloride, we call that a formula unit because it's like the basic, simplest unit of this lattice structure. But there's actually no such thing as like NaCl molecules floating around the way that there are with water. So that's just a terminology thing that I actually think I explained in a previous session because some people were confused in the homework because when it mentioned ionic compounds, it would say like instead of what's the molar mass or how many molecules of something are there. It said how many formula units were there, and that was confusing because people are like, what's a formula unit? So now you know. Okay, I guess to go to page 2, I have to share them like one at a time. There we go. Technically not great at this program. All right, so quick practice question for you here. Are the following compounds ionic or covalent? Somebody turn on your mic and tell me, how could we tell if they're ionic or covalent just by the molecular formula? How would we know?
By the numbers?
Ionic usually
Not by
has
the
a
numbers.
metal and a nonmetal.
A metal and a nonmetal. I heard someone say that. So remember, ionic is a metal plus a nonmetal, and covalent is a nonmetal plus a nonmetal. So simply by looking at the formulas, we can tell whether something is ionic or covalent. So H2O, is that one ionic or covalent?
Covalent.
Yep. Hydrogen and oxygen are both nonmetals. Even though hydrogen's on the left side of the periodic table, it's that one loner that's actually a nonmetal. What about KBr? Ionic or covalent?
Ionic.
That one is ionic because potassium, K, is a metal, and bromine is over in group 7. It is a nonmetal. CH4.
Covalent.
Is covalent. So for a lot of these, you'll just be getting a lot of practice using your periodic table, finding where things are. PCl5, phosphorus and chlorine are both nonmetals, so this would also be covalent. And copper fluoride, what about that one?
Ionic.
Yes, copper is a transition metal, and chlorine is a nonmetal, so this one would be ionic. So there may be some simple questions in the homework just asking you to identify compounds as ionic or covalent based on their formula, and the rule sort of that you're going off of is this rule here. All right, so now we know how to identify ionic and covalent compounds. Now we're going to learn how to name them. And there are very systematic rules for naming chemicals. So there are a lot of chemicals that have common names. So for example, H2O, we all know is water. We call it water. All right, that's the common name. But there is a systematic name, and the system is, I can never remember what it stands for, IUPAC. IUPAC. I should just look it up one of these days. Something about the International Union of something for chemistry, and they make all the naming rules. So all of the rules we're about to learn on how to name things. So the systematic IUPAC name for water is actually dihydrogen monoxide. And if you click on that link in the PDF, it'll take you to a funny website that talks about all the dangers of dihydrogen monoxide, because there's all this like chemical, people are afraid of chemicals, and anything that has a chemical name, they're afraid of it, and they think it's toxic. And so it's this funny website about, you know, have you heard of dihydrogen monoxide and the dangers of dihydrogen monoxide? Like, if you breathe it in, you could die. And if you like inject it in your veins, you could die. Like all this stuff, all the ways that you can die via water. If you don't get enough of it, you can die. If you get too much of it, you can die. Like it basically makes water sound like this deadly chemical. And water can be deadly. Anything can be deadly, I suppose. But it's also, of course, incredibly vital for life. And so it's very tongue-in-cheek and funny. all about the dangers of dihydrogen monoxide. NH3, common name ammonia, right? But the technical systematic name, IUPAC name, would be nitrogen trihydride because it's made of 1 nitrogen and 3 hydrogens. So for covalent compounds, the naming system is actually makes a lot of sense. Basically, when we're naming these compounds, and the ones we're going to be naming are what are called binary molecules, binary covalent compounds. That means they're made of 2 elements. So covalent compounds can be very large. And if we get to a section on organic chemistry next semester, we'll learn how to name some of those larger molecules. But right now we're just focusing on small binary compounds made up of 2 elements. So basically the structure is that you use a prefix in front of each element name that indicates how many atoms of that element are in the compound. And so for the first element, you use a prefix and then the element name. And then for the second one, the second element, you use a prefix, the root of that element, and then it ends in "ide." All right, so for example, we had nitrogen trihydride. So nitrogen, we didn't end up needing a prefix for that. And that's because there's only 1 nitrogen, and there's this sort of one exception here that if there's only 1, you don't need a prefix for the first element only, not the second element. That rule doesn't apply there. So for water, we have H2O, dihydrogen, there's 2 hydrogens, and there's 1 monoxide. So for this example here, carbon dioxide, we would say, I just said it, carbon, we don't need a prefix of 1. We don't need the prefix mono because it's the first element, and that's sort of the exception to the prefix rule. And then the second element is oxygen. There's 2 of them, so we're going to use a prefix di for 2. And then instead of having dioxygen, we say dioxide. So we end the name with that suffix "ide." So the different prefixes that are used are mono, which is 1, di is 2, tri is 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona 9, and deca 10. So let's do some practice naming some of these examples. So this first one here, N2O5. All right, so what prefix will we use for nitrogen?
Di.
Yes, so we have, come on, stylus, dinitrogen. And then what would the prefix be for the oxygen?
Penta.
So we're going to call it pent. We'll drop the A because octa starts, because penta O would be weird. So pentoxide. The next one, we have 1 oxygen, but since it's the first one, we don't have to write mono. So we can just say oxygen. And then there's 2 fluorines, so it'll be difluoride. And then what would the last one be?
Tetraphosphorus heptasulfide.
Perfect. Tetraphosphorus heptasulfide. All right, so whenever you're learning a new language, you always want to study it and practice it both ways, right? Like Spanish to English and English to Spanish. So we're not just going to practice naming things, we're also going to practice writing formulas from the names. and they really give you very good instructions. So carbon tetrachloride tells us there's 1 carbon and 4 chlorines. All right, what would the formula be for dichlorine monoxide?
2ClO. I mean, sorry, Cl2O.
Yes, very good. What about dinitrogen monoxide?
N2O.
Yep. And then the last one, phosphorus pentachloride. I'll do that one. How many is penta?
5.
5.
Good. Okay, so covalent compound naming is, I think, easy. It's very straightforward. It's using these prefixes just to tell you how many atoms of each element are in there, so it's all in the name. Ionic compounds are a little bit trickier, and that's what we're going to move on to now. And the next page, page 3. All right, so now we're going to be talking about ionic compounds. So remember, ionic compounds are basically compounds made up of cations and anions. Cations are positively charged, anions are negatively charged, and opposite charges attract. That attraction is the ionic bond. So even though they're made up of charged particles, ionic compounds are neutral, okay? That's a key thing to know. It's key for being able to form ionic compounds. So essentially the positive the positive cations and the negative anion charges need to cancel out, or they need to add up to 0. So there are 2 types of ions that we can have, technically. There are monoatomic ions. What do you think monoatomic means?
1.
Yeah, 1 atom. So they're ions from 1 atom. So basically any atom of an element from the periodic table, like sodium, potassium, calcium, magnesium, oxygen, you name it. One of those atoms gains or loses electrons, then we have a monoatomic ion. And we went over that and how monoatomic ions form and the charges they have back in chapter 3. And I even went back and looked at page 15 of the chapter 3 notes, if you want to go back and review that, on how to know what a charge is going to be, how many electrons an atom will gain or lose, and what charge it will have, just using the periodic table. There's also compounds, basically, that can gain and lose electrons, and we call those polyatomic ions. Poly meaning what? Who knows?
Multiple.
Yeah, that means many. So a polyatomic ion has multiple atoms in it, more than 1 atom. So I didn't make this 4 a subscript, and I should have. This is PO4. That 4 should be a subscript, meaning it's a phosphorus and 4 oxygens, and it's a molecule, a covalent molecule that has gained electrons and become an ion. So there's a whole table here, and I also posted this table on next to the notes, so you could print it off separately and have it for you. I don't make students memorize this. I always provide it on tests. So, but it's still good to really familiarize yourself with it. And the couple that I tell you to memorize, because otherwise you'll just get confused a lot, are hydroxide, which is right here, and cyanide, which is right here, and ammonium, which is right here. Because those 3 sound like elements that you would find on the periodic table. And then you'll sit there looking for the element ammonium on your periodic table and you won't find it. So really, those three, memorize those. You need to know that those names are names of polyatomic ions, not monoatomic ions. The others are pretty straightforward, or they have a naming pattern. A lot of them end in "ate" or "ite." And some of these I just noticed are not polyatomic ions. So there's some non-polyatomic ions on this table. So when we name ions, naming ions is actually pretty simple. Main group ions, so remember main group elements are ones in columns 1A, 2A, and 3, 4, 5, 6, 7A. So skipping over, not including the D block of transition elements. So for those guys, their metal cations, we just add ion after the element name. So sodium ion is just sodium ion. So calcium 2+ would be a calcium ion. That would be its name. Easy peasy. For the transition metals have this ability to lose different numbers of electrons, so they can form multiple ions. So calcium really only forms a 2+ ion. It only loses 2 valence electrons, but iron can lose 2 or 3 valence electrons. Because of that D sublevel, that D sublevel can do some funny things because that 4s and 3d kind of overlap. The electrons can do funny things and end up with multiple different ions. So if we say an iron ion, we have to specify which iron ion, because there's an iron 2+ and an iron 3+. So we specify it by using a Roman numeral to indicate the charge. The iron 2+ ion is the iron 2 ion, and this one would be the iron 3 ion. So that Roman numeral is actually telling us what the charge of the ion is. For nonmetal anions, these are, we use the word root and then we use that suffix "ide" again. So the chlorine, when chlorine gains an electron, it becomes a chloride ion. When oxygen gains 2 electrons, it becomes an oxide ion. And that's kind of familiar from our naming of covalent compounds, which involve nonmetals and end in "ide." So it's sort of consistent here. And then polyatomic ions all have their own names, but many of them end in "ate" or "ite." And that's key to remember, because if you see something like sodium phosphate, all right, then you should see that 8 and realize, oh, that is going to be, we're not talking about an ion of phosphorus, we're talking about a polyatomic ion, because it ends in 8, and I should go look up that polyatomic ion on my table. So, next page. So when we're writing ionic compound formulas, remember ionic compounds, although they're made of charged bits of ions, the charge must be equal to 0. When you add up the negative charges and the positive charges, they must equal 0, so that ionic compounds are neutral by definition. They have no charge. Another rule for writing ionic compound formulas that you may or may not have noticed already is that the metal is always written first. The cation or the metal is always going to be written first, and then the anion is written second. So when you're identifying if something is a ionic compound or a covalent compound, that if that first element is a metal, you don't have to look at the second one. If the first element's a metal, then you know for sure that it is a ionic compound. The other rule is you always want to write it in the simplest possible ratio. So for example, NaCl is the correct formula All right, so it would be improper though to write Na2Cl2, even though that would have it's the same ratio of sodium to chlorine. It's not the empirical formula essentially. So you always want to write the simplest empirical formula for an ionic compound. So some other examples that I have are potassium and fluorine. Potassium has a 1+ charge. It's in group 1 on the periodic table. Fluorine has a -1 charge, so they'll combine to form Kf, potassium fluoride. Magnesium is in group 2, 2 valence electrons. It'll lose those for a 2+ charge. Oxygen's in group 6, so it will gain 2 electrons for a 2- charge. These two charges cancel out. 2+ plus 2- equals 0. So we have a 1-to-1 ratio of magnesium and oxygen in magnesium oxide. And then here's another one, aluminum and a polyatomic ion here, phosphate, combine. Their charges cancel out, so they combine to form the ionic compound aluminum phosphate. All right, so it's easy when the charges are equal and opposite, when the charges have the same magnitude, 3 and 3, 2 and 2, 1 and 1. But if the charge numbers are different on each ion, then we have to do a little bit of math in order to make sure that we're combining them in a way that their charges cancel out. And there's something called the crossover shortcut method. And in this method, the charge of each ion becomes the subscript of the next ion. So I'll show you how that works in these examples here. All right, so here we've got calcium and chloride. Calcium has a 2+ charge, chlorine has a 1- charge. So if we put that 2 down here and we put that 1 down here, we get 1 calcium and 2 chlorines, calcium chloride. The other way to think of that is to just do the math. So NH4 and S2, we have a 2- charge, but we have 1+ charge. So the only way that we can get a neutral ionic compound is if we have 2 of these guys, because 2 positive, that would be 2 times the 1 positive charge, or a total of 2+ charges, and the 2- charge there. So this should actually, there should be a 2 subscript right here. NH4 subscript 2 S. Since NH4 is a polyatomic ion, we have to put it in parentheses because we want it to be clear that we have 2 NH4s, not 2 N's and 8 H's, but 2 NH4s. It's a single unit. So let's somebody try this one. This one is potassium. This should be a superscript. It's the charge. So it's a 1+ charge on the potassium. And the carbonate, CO3, has a 2- charge. Again, I have some editing issues here. So 2- charge, 1+ charge. So what will the formula be?
Be K2CO3.
It would be K2. We need 2 of the potassiums because each one has a 1+ charge, and CO3, just one of them because it has a 2- charge. And together that would have a total of 0 charge. The charge would add to 0. Here's another one where I messed up formatting. So this is aluminum, and aluminum has a 3+ charge plus the hydroxide ion. I don't even know why I wrote that. I think that was a typo, but it kind of makes for a fun problem here. So aluminum hydroxide. Hydroxide is one of those polyatomic ions that you have to look up on that table, and it's OH-. So aluminum 3+ and OH-, we need 3 of these guys in order to balance out the 3+ charge of the aluminum. So we would have 1 aluminum and 3 hydroxides, and of course we need to have parentheses around that polyatomic ion so that when we put our 3 there, if we did it like this, all right, that would be a different molecule, it would only have 1 oxygen and 3 hydrogens. So that's why it's important to always put parentheses around a polyatomic ion. There's some more examples over here. So here's aluminum and oxygen. They have different charges. All right, and that crossover method says the 3 from the aluminum will become the subscript on the oxygen, and the 2 from the oxygen becomes the subscript on the aluminum. And that's just sort of a simple shortcut to doing the math. Same thing here, we can do this here. That lithium, the 2 from the charge on the sulfate, and the 1. So we get Li2SO4. We just have 1 of them. So somebody tell me what this formula will be. If we combine, oh my God, what a mess. Barium has a 2+ charge, and oxygen has a 2- charge. So what will the formula be?
BAO.
Yep. Good. Not Ba2O2, but BAO. That would be the simplest form. They cancel each other out. Okay, so when it comes to making ionic compound formulas, you need to be able to know the charges on the ions, and you need to be able to essentially balance them, have them cancel out to 0 in order to form the right ionic formula. So the other thing is that with ionic compounds, calcium and chlorine, there's only one element that they can, or compound that they can actually make together, and that's CaCl2. There's no such thing as CaCl or CaCl3 or Ca2Cl3. None of those combinations exist because none of those would follow the rules for ionic compound formation. None of them would end up forming a neutral compound. So because of this, we don't need to use prefixes when we are naming ionic compounds, because calcium chloride, there's only one way that calcium and chlorine can combine to form an ionic compound. So by saying calcium chloride, we should be able to figure out the formula. So when we name ionic compounds, it kind of seems easy. Naming them is easy because we don't need to use any prefixes. What can be tricky is going backwards from the name to the formula. So here we go. KBr would just be potassium bromide. And it's coincidental that there's one of each. So it would be the same thing if we were naming a covalent compound. But look here, this one has 2 sodiums and 1 sulfate, but we just call it sodium sulfate. It's not disodium sulfate. So the rules are different. There's no prefixes when we are naming ionic compounds. MgF2 is just magnesium fluoride. I should say it's the cation name and the anion name, and it ends in "ide." All right, so KCN. Cn is a polyatomic ion, cyanide. So this would be potassium cyanide. And BaCl would just be barium chloride. And sodium phosphate, or Na3PO4, is sodium phosphate. All right, so these were all elements that had main group metals. It's a little bit different if we have a transition metal, because remember, transition metals use those Roman numerals, and so we have to make that part of their name. So, for example, we talked about iron having 2 possible charges, 2+ or 3+. So if we want to name this guy here iron chloride, we have to indicate which iron we're talking about. And in order to do that, we have to do a little backwards math to figure out what the charge is on that iron. So the chlorine, right, this molecule is made up of iron and chlorine, not molecule, this ionic compound is made up of iron and chlorine, And we have 2 chlorines, each with a -1 charge. So there's a total of -2 charge from the chlorine. And the iron, we have 1 iron, and we don't know its charge, so we can give that an X. But we know that its charge needs to add up to 2+, because the charge from the iron and the charge from the chlorine need to sum to 0 in order for this to be a kosher ionic compound. So we can solve for X, and X therefore equals +2. All right. So that means that this is the iron 2 ion. So we would call this not iron chloride, but iron 2 chloride. Iron 3 chloride would look like this, right? So it would have a different formula. And that charge, a big mistake that students make if they're going from the formula to writing the actual or they're going from the name to the formula, is they think that that 3 indicates how many irons there are. So they want to do something like this. My stylus keeps dying. So they want to put a 3 there. Okay, but that's not what the 3 means. It's not the subscript, it's the charge. It means it has a 3+ charge. So now we're going to do some practice, and then I'll be sending you on your merry way to do some practice in the homework until you have this down pat, and I'll be testing you on it on the quiz. So let's try out this one here. It's copper sulfate, but copper is a transition metal, and transition metals need a Roman numeral. What Roman numeral are we going to have on that? So sulfate is a polyatomic ion. You'll have to look that up. What's the charge on the sulfate?
-2.
2-.
Yep, so the sulfate has a -2 charge. All right, so what is the charge on the copper ion?
2+.
It must be 2+ to cancel out that 2-. So this would be called copper 2 sulfate. And what about this one here? We have copper and oxygen. We don't know, copper is a transition metal, so we know that there's multiple, it could have multiple charges. So we've got to start with the charge on oxygen. What's the charge on an oxygen ion? That you would use your periodic table for. What is it?
2-.
Good. Come on, stylus. There we go, 2-. So then what must the charge on those copper ions be?
2+.
There's 2 of them though, so if it's 2+, then we'd have a total of 4+ charge.
So then 1+.
Yeah, so 2 times 1, since there's 2 of them, that the charge must be 1+, so that we have 2 positive charges and 2 negative charges. So this is copper 1 oxide. All right, so there's just a couple more problems here. So we've been doing a lot of writing the names from the compound formula, but in this practice problem, we're going to write the formula from the names. And this is where people get tricked a lot too. So aluminum sulfide. If we're thinking covalent compounds, we're thinking, oh, there's no prefixes. So it's just aluminum, and sulfide is sulfur. So aluminum sulfide, ALS, not Lou Gehrig's disease. But that's not the case, okay? because when writing out formulas from names for ionic compounds, we always need to indicate what the charges are on those ions. So aluminum is group 3A. It has a 3+ charge. Its ion has a 3+ charge. Sulfur is in group 6A. It has a 2- charge. All right, if we're combining the two of those, what ratio will we have? What groups will we have on the aluminum and the sulfur?
It'd be Al2S3.
Al2S3. Very good. So we could use that crossover method, and the 2 becomes the subscript on the aluminum, and the 3 becomes the subscript on the sulfide. If we do the math, all right, 2 times +3 plus 3 times -2 is going to give us 0, because that will be +6, that will be -6, and that will be 0. So that's why that is the correct formula for aluminum sulfide. So aluminum sulfide can only ever be Al2S3. There's no other ionic compound that can form between those two. Iron 3. I like to write out the ions sometimes. So iron 3 means it's an iron with a 3+ charge. And nitrate, the 8, tells me that it's a polyatomic ion. And I want to go look on that polyatomic ion table. And I find nitrate, and it's NO3, and it has a 1- charge. So these two are going to come together. And since iron has a 3+ charge and nitrate has a 1- charge, we essentially need 3 nitrates in our compound in order to cancel out the charge of the iron. So we'll have iron and then 3 nitrates. Since nitrate is a polyatomic ion, we want to keep it all together in the parentheses. We write our 3 outside the parentheses there as a subscript. So that would be iron 3 nitrate. Calcium phosphate. Again, I'm going to write out my ions. Calcium, group 2 element, so it has a 2+ charge. Phosphate tells me it's a polyatomic ion, so I'm going to go to my table and find phosphate. And I believe it has a 3- charge. Can somebody check and confirm that?
Right.
Cool. So when we combine them, we could do the crossover technique here. That calcium takes the 3 from the phosphate takes the 2 from the calcium. So we get Ca3 and PO4 So we need to put our PO4 in parentheses and then put 2 subscript outside the parentheses. So the key with polyatomic ions is you never want to break them up. You just want to keep them together. They are one unit, one particle, one thing. Copper 1 sulfate. Copper, Cu, and the 1 tells us it has a 1+ charge. Sulfate, 8 tells us it's a polyatomic ion. I look it up on the polyatomic ion table, and I see it has a charge of 2-. So when I combine these, I'm going to need 2 coppers to have a 2+ charge in order to cancel out the 2- charge of the sulfate. So I indicate that in the formula with a subscript of 2. And I don't need parentheses on my sulfate because I only have one of them. I don't need to put a subscript there, so I don't need the parentheses. Silver oxide. Silver, guys, is in the transition metals, but it happens to only have 1 ion. And its 1 ion has a +1 charge. So because of that, we don't have to use Roman numerals for silver. And you'll see that in prompts. It's just something you have to memorize. Zinc is also in that boat. Zinc has only a 2+ charge. So even though zinc and silver are transition metals, you'll see that they're named without Roman numerals. I won't put those two on the test because they're sort of exceptions to the rule. And I like to test students that they know the rules, but I just throw in and tell you about the exceptions so you're aware of them, but I won't try to like trip you up with exceptions like silver and zinc. So if you come to a problem like that and you're like, well, what's the charge on silver? It's +1. Oxygen, or oxide, that "ide" usually tells me, okay, that's an element. I should go look on the periodic table for what element has the root ox, and of course that's oxygen. So we're talking about an oxygen ion, which has a 2- charge because it's in group 6, 6 valence electrons. It's going to gain 2 electrons to fulfill the octet rule. So if I have silver with a 1+ charge and oxygen with a 2- charge, I need 2 silvers for every 1 oxygen. So Ag2O would be silver oxide. And then lastly, copper 2 carbonate. Copper 2 means it has a 2+ charge, and carbonate, 8, tells me I'm working with a polyatomic ion. I look it up on the table, and it's CO3, and it has a 2- charge. And finally, we have one where the charges are already equal and opposite, so 2+ and 2-. So just copper carbonate would be the formula. All right, so some ionic compounds bind to water molecules and are sort of permanently bound to water molecules. And when they're in that state, we say that they are hydrated, or we call them hydrates. You take a salt. So ionic compounds, here's another thing I should mention. Ionic compounds, I don't know where you want to put this. This is just a random spot. Ionic compounds are called salts. All right, we tend to think of sodium chloride as being salt because it's the salt we use most often. But any ionic compound is called a salt. The salt that you use on the road in the wintertime is not sodium chloride. I think it's calcium chloride or magnesium chloride, and you don't want to eat it. Other salts, Epsom salt is actually magnesium sulfate. This compound right here is Epsom salt, and it happens to be a hydrate. So any ionic compound is considered a salt. So when I use the term salt, I'm talking about ionic compounds. So some ionic compounds, salts, like to bind to water molecules. And for example, Epsom salts are actually hydrated. There are water molecules bound up in those crystals of the magnesium sulfate salt. So we name these, the naming system for this is simply to use a prefix to indicate the number of waters in the hydrate. I don't know what that was, but I can't erase it. And then to indicate the waters, we say hydrate. So this would be called magnesium heptahydrate. Sorry, magnesium sulfate heptahydrate. So we could do a couple more problems practicing naming hydrates. Copper chloride. I just gave it away, I just said it. Right, copper. Copper is a transition metal though. So it's copper chloride, but because copper is a transition metal, I know I need to have a Roman numeral there. So I need to figure out which Roman numeral to put. Chloride has a negative charge, -1 charge, and there's 2 of them. So there's a total of 2- charge from the chlorides. So the charge from the copper needs to be 2+ to balance that out. So it's copper 2 chloride, and there's 2 water molecules, so it would be a dihydrate. We used with covalent compound naming. And then this one here, barium hydroxide octahydrate. So barium hydroxide would be what formula?
BaOH2.
Good. So hydroxide is a polyatomic ion, OH minus. Barium is a monoatomic ion and it has a 2+ charge. So the formula would be BaOH2, and then we draw this little circle, and we indicate the number of water molecules. Octa is what?
8.
Yeah, 8H2O. So if you have a salt that is a hydrate, you do have to include those water molecules. Like if you were calculating the molar mass of a hydrated salt of barium hydroxide, you would need to calculate the mass of the barium hydroxide, but also the mass of the 8 water molecules. If you were asked to find the molar mass of some hydrate. And that's all I have for 4A, because this is a topic that just needs a lot of focus and practice, and I wanted you guys to get that in the first half. So I did actually change up the homework. Exit out of that. Tonight I went, because I decided to leave out talk of electronegativity, and we'll do that in the next part of the chapter. So I took out any electronegativity problems and I added a couple more problems about finding the charge on ions. So if you finished the 4A homework already, go back because there's a few new problems, but they're pretty simple.
Professor.
So,
Professor?
what questions do you have? Yes. Yes, guy.
The hydrated ionic compounds, are those linked together, bonded together by hydrogen bonds?
No, it's more like water molecules get trapped in the salt crystals.
Oh, okay.
They become sort of embedded in the salt crystals. So like if you think of that lattice structure that that the sodium chloride made, if you think of a bunch of water molecules kind of stuck in there, that's a hydrated salt.
Okay, thank you.
And I guess technically the bonds that hold them together are called ion dipole bonds. Alyssa and Liz, I think you both showed up after I started gabbing. Did you have any questions or did you miss anything?
I didn't have any questions.
Okay. How about you can do this? How do I want to do this? Well, if you're willing to share in the chat, on a scale of 1 to 5, 1 being this is super easy for me because I've maybe taken chemistry before, to 5, I'm not sure what you're talking about. This makes no sense. How did you feel about this chapter 4A? Okay, good. Just make sure you practice it, because careless errors, getting the covalent naming rules mixed up with the ionic naming rules is sort of classic mistakes that are made. So the homework might feel a little tedious because there's just lots of problems. And if it's super easy for you, you'll just breeze through them. And if you're getting them wrong, you'll realize, okay, maybe I need to practice this a little bit more. But I feel like it's very doable. So go off and do your chapter 4A homework if you haven't already. I notice a lot of you have turned in the flame labs. Those are due tonight. And any questions about the flame test lab, actually, while you're here? No? Alrighty then. I guess it's time to end the recording and say goodnight.